Hello, everyone, and welcome back to Concordia University's Fourth Space. Thank you for joining us once again for Space Day for today's talk, Hybrid Engines, Liquid Logic. We would like to begin by acknowledging that Concordia University is located on unceded Indigenous lands in Tiohtià:ke, Montreal. We respect the continued connections with the past, present, and future in our ongoing relationships with Indigenous and other peoples within the Montreal community. Here at Fourth Space, we work with our university community to mobilize knowledge by co-creating daily activities that examine research questions and projects in development across the university. We are running today's event as a live stream Zoom meeting. So for those of you joining us on Zoom, we welcome your comments and questions with a raised hand via the chat. And for those of you in the space, if you'd like to participate, just let us know by raising a hand and we'll be sure to get a microphone to you. With that, it is my pleasure to hand the mic over to Dr. Jerin John, Assistant Professor, Mechanical, Industrial, and Aerospace Engineering. Dr. John, welcome.
Hello. My name is Jerin John. I'm an assistant professor here at Mechanical, Industrial, and Aerospace Engineering. I joined Concordia in 2023 May. So a bit about myself. I did my PhD in South Korea. I also did my postdoctoral training also in South Korea. So my research background was a bit on rockets, propellants, and fuels. So fuels are same as that of the propellants in case of the rockets. And then some work experience on the rocket engine, actually. So I did work with a company called Perigi Aerospace, which is also a small startup company, now focusing on developing LNG LOX-based liquid propellant rocket engine. So if you're new into this kind of a rocket engine stuff, let's start with the beginning, like the very basic. So my topic of discussion today here is about the hybrid engines. So you would have heard about hybrid vehicles in terms of cars. What are the differences? The basic difference is they have an internal combustion engine which burns the gasoline, produce some power. They also have some batteries which also produce some power so that the cars can move. So sometimes it works standalone, like either electric batteries or run by the gasoline or combined together to produce cumulative power. That's the same thing happens for the rockets. It's not a one-liner answer. It's a bit challenging to address that when you compare it with the internal combustion engine. So hybrids in general are classified based on Okay. So basically what happens in the rocket engine is, like, unlike the gasoline or gasoline engines or internal combustion engines, you carry fuel. But in rockets, you carry fuel and oxidizer. What are oxidizers? Oxidizer is nothing but air. In case of rockets, they are not air. They are either liquid oxygen or pure 100% oxygen and some other products or chemicals that supplies oxygen for combustion. So in rocket engine, generally what happens is you store fuel and oxidizer separately or together. So fuel and oxidizer will be passed on to a place where reaction happens. We call it as combustion reaction. And then this energy produced is being accelerated through a kind of a device called nozzle to produce thrust. So chemical rockets are basically classified into different categories. It could be solid rocket motor or solid rocket liquid propellant engines, gaseous propellant rocket engines, hybrids. So these are the classifications what we generally have for rockets. In the layman term, basically these classifications are based on what is the phase. Phase means liquid, solid, gas. All this, based on these phases, the rockets are being classified. So today I'm going to talk about a bit on hybrid propellants. Why hybrids? Why not solids, liquids? Like Space Concordia is working on liquids. Some part of a team is also working on SRMs. But why hybrid? Like what is the reason behind we choose hybrid? So it's not going to replace the existing rocket system. It's also not going to replace the liquid system, what Space Concordia is working on, or not the solid rocket motors. It has advantages and disadvantages. Some of the advantages are to overcome the liquids. Some of the advantages are to overcome the solids. But it is never a replacement for any of those. So hybrids in general means fuel is either in solid state and then oxidizer is in gaseous or liquid state. They are referred as the classical hybrid configuration. And then there is an inverse kind of a configuration where fuel is in the gaseous or a liquid stage and the oxidizer in the solid state. So these are the two different classifications under the hybrids. So let's look into the hybrid propellants. What are their merits? What exactly is the issue with them? Why you can't see not many rocket companies working on hybrids or not any launch happening with the hybrids, but you can see a lot on solid rocket motors and liquids. So we'll look into it a bit and then see what is current research which is happening around the hybrid world. So again, hybrid uses both solid and liquid. So it's a mix of two different classes of fuel and oxidizers. That's the reason why it's called hybrids. So if you know the architecture behind the solids, basically solid rocket motor is just simple as this part, where the fuel is being stored in the hybrids. So in solids, what generally is going to happen is you have fuel and oxidizer, which is present inside this chamber. So the system is very simple. That's simple design compared to all the other liquid engines or all other rocket engines. But in case of hybrid, you have oxidizer, which is in a different phase and it is separated from the fuel, just mimicking a kind of similar technology what we have for the liquids. So the simplest part is if you wanted to stop the engine, you can simply cut it off with this valve, just like liquids. Liquids, if you close this valve for the fuel and oxidizer, you terminate the thrust. Similarly, if you adjust the valve a bit, you can adjust the thrust as well. So it has some advantages of the liquids, some advantages of the solids, and some disadvantages. That disadvantage is something which is not letting the people to choose to go with the hybrids. I could bring the analogy, which is kind of similar with what we have seen in the electric cars. When electric cars were first introduced in the market, it was not absorbed by the people because it looked very bad. Like the design was very bad, and also like the miles it go is like literally less than 20 miles. But now when you look at the hybrid system or electrical cars, it's equally or better than that of the conventional internal combustion engines. So hybrids are picking up the pace. Definitely, it will reach to a point where the industry would adopt, but it will never be a replacement for the liquids. Some of the benefits what we have with the hybrids are they are inherently safe because the fuel and oxidizer are stored separately. You can cut it off anytime you want. And then it has a capacity to throttle a bit, like you can change the thrust, depends on your usage or depends on your requirement. The only problem what the hybrid faces is their very bad burning rate. But before getting into it, let's look at the history a bit regarding the hybrid rockets. So hybrids, the concept started in early 1930s, just the similar way how the liquid propulsion system were introduced. So many examples we have here which used hybrids but never flown as like a flight vehicle. And the reason one is that like a lot of startup companies right now is focusing on to build hybrids. Any particular reason why is just that it's very simple in terms of design and the developmental cost is much lesser than that of the liquid system. So one such example is the High Impulse. They are based in Germany, working on paraffin wax LOX combination. And then we have Glenmore Technologies in Australia. They are also working on the same combination with the same kind of a thrust. And then we have Space, which the company has bankrupted. It's based in Ontario. They also worked on similar technology like paraffin wax and liquid oxygen. And now Reaction Dynamics. Reaction Dynamics is a space startup company, again, based in Montreal. They are also working on something, hydrogen peroxide as an oxidizer instead of LOX and paraffin wax. They're claiming that they are hypergolic. So when it comes to the propellants, hypergolic means that you don't need a dedicated ignition system. Fuel and oxidizer meets and it burns spontaneously without any ignition source. So understanding the hybrids combustion is very important to understand why it's not been used or why it's not been developed thoroughly or not been used as a launch vehicle backbone, like design backbone. The major issue lies between underneath the solid combustion, like how the fuel is being combusted in that high pressure environment inside the engine. So the first, when a solid fuel burns, it has to undergo melting, and melting to become vapor, and then liquid to vapor, and then vapor mix up with the oxidizer to produce the final energy output. So there is a 4-step process involved in the burning of the solid fuel. This is the major reason why the burning of the hybrid rocket fuels like solid fuels are very slow compared to that of the liquids. So if you compare it with liquids, a tiny droplet would convert from liquid to gas and then produce the energy. Here it goes to solid, liquid, gas, and then combustion. So the step involved is 4 instead of 3. That is making the fuel very slow in burning compared to that of liquid. Therefore, the performance regression rate, what we call, is very low compared to that of the hybrids. So this involves a kind of a different combustion compared to that of the solid rockets. Solid rockets are generally fuel and oxidizer, which is present inside the fuel itself. So when you ignite, the mixing happens there and it just burns rapidly. But in case of the hybrid, the major issue is you are supplying oxidizer from outside and it is more diffusion control. So if you have some kind of an understanding between a background about the combustion process involves 2 steps. One is like a diffusion, one is like a premix. So our cooking ranges that uses the gas, is kind of like a premixed flame. It burns very fast. But the conventional fuels that we use in the domestic application long time back, maybe 50 years back, uses kerosene, and it is very slow. So you can compare the rate at which you could cook or how fast you can cook. The same process here. The diffusion process or diffusion-based combustion is kind of a slow compared to that of the premixed-based combustion. So in hybrid, that is the backbone of the combustion process, which is kind of very slow. So what is happening in the current setting, like what people are doing? So they try to increase the burning rate or regression rate by invoking a couple of mechanisms so that the burning area would increase and then you will have a higher power output. So some of the factors are here. Grain means how the fuel is being shaped inside the combustion chamber. And sometimes they increases the mass flow rate at which the oxygen is being supplied. Sometimes they increases the combustion chamber pressure or length or cross-sectional area. So one of the common thing is the grain composition, like how do they mix the solid fuel and keep it inside the combustion chamber. As here, you could see a multiple pores. This is actually the solid fuel. And the oxidizer would be passing through these holes, and these holes would undergo diffusion combustion reaction to produce thrust. So a couple of performance parameters that you could expect from the hybrid configuration if you change the grain structure is what, if you look at this kind of an image. So very simplest one is people use this hollow multiple porated solid fuel so that the regression rate would increase based on the surface area. So we have multiple kind of a design and have been tested and validated just to address how we can increase the burning of the solid fuel so that it is at least matching it to the solid fuels or liquid fuels. But these are lab level testing, and this is what we could achieve. And the performance is nowhere near to what solids or liquids that are giving us. So that's the reason why hybrid is not that attractive option until now. Now, there is second class of a fuel. So earlier I was talking about the solid fuel that are rubber-based, just pure solid. It could be a wood, coal, or anything that are solid. But now another kind of an interest that is picking up in the market is the paraffin-based fuel. That's there from 1970s. So paraffin is nothing but your candle wax. So if you look at candle wax, what is happening? If you just light it up, it melts into liquid, and then that vapor gasifies to produce the flame, and that heat energy in the in the rocket has been converted into thrust. So paraffin wax has an advantage compared to that of the other solid fuel because the other solid fuel requires at least 150 degrees Celsius to become melt and then liquid and then gas. But paraffin wax is very simple that you just need 40 degrees Celsius so that it becomes liquid. So the step process involved is 4, but the amount of energy required for them to gasify compared to that of the rubber-based fuel is literally low compared to, that's the reason why paraffin wax is kind of an attractive option. So if you look at how many companies that work on hybrids recently, most of them work on paraffin because there are no alternative for paraffin compared to that of existing or past hybrid fuels. So the physics behind is that like when the fuel grain, which is in the liquid solid stage, melts to form liquid, these liquids form tiny droplets and mix up with the incoming oxidizer to form the flame. This is a kind of concept which is similar to that of liquid propellants. So you have liquids, two liquids coming in, mix up well with each other to produce the diffusion flame. So that's the reason why paraffin wax has kind of like a higher burning rate or regression rate compared to that of the normal solid fuels or rubber-based fuels. Now, as the talk suggests liquid logic, like hybrid engines and liquid logic. So I'm not going to talk about the paraffin wax because it's there already and people are working on it. But my objective is to bring a bit of a different spin altogether for the liquids. So the background is I am taking something like liquid fuel, which is existing in the nature, or it's been already used in liquid engines. One such example is a kerosene, which the Space Concordia already used. You take kerosene and convert them into solid. Convert them into solid, or in here, I have used ethanol as a demo to convert into a solid case. But solidification is not that you convert the liquid kerosene or liquid ethanol completely into solids. I am going to create a matrix like this, and the ethanol will be suspended inside as a liquid ethanol. So the fuel has a phase of a solid, but overall structure would be solid, but the ethanol, which been used for this purpose, would remain as liquid. So now you get what would be the advantage of this one. Our advantage is actually derived from paraffin wax. Paraffin wax requires 40 degrees Celsius to melt and liquid and then diffusion flame. Here, liquid itself is present in the solid matrix as liquid itself. So when they burn, what is going to happen is liquid gasify to form the thrust or diffusion flame. So you are again converting that 4-step combustion process into a 3-step combustion process using this mechanism. So this is one such example. Of course, I have made a big claim that only 3-step process. Then I have to prove that this is not something equivalent to paraffin wax. I should be expecting a performance at least same as paraffin wax or little bit better than paraffin wax, right? Or else what is the point of this research? So I started with this as a motivation, and then we went on further to study this fuel's characteristics in detail. So one such example is, this is one kind of a simple equipment where you test your fuel. You take a small chunk of a fuel, you burn it, and you measure the time in which it takes to burn. So we have a solid ethanol, which is present in here, and you pass oxygen as a gas onto the surface of the solid to see how fast it is burning. So what I found was, so a couple of results, which I'll go detail into one particular chart to make it very simple. So we have this paraffin wax, which is a standard one that has been used in the hybrid rockets. And then boron wax and paraffin wax are commonly used again. And these first 4 samples are something which we have developed for the research purpose. So we passed oxygen at different rates and observed how fast it is burning. So what we found was the lower flux region, I mean, like when the oxidizer flux is too low, you have a performance of this solid fuel equivalently good as that of the paraffin wax. At higher flux region, some of the samples shows a better regression rate compared to the paraffin, and some doesn't show that evidently. Like for example, over here, we have aluminum based, like you embed little bit aluminum particles inside the fuel, and the way in which it burns is significantly high compared to that of the standard paraffin wax fuel. So the major reason is this, that the combustion is no more a 4-step process in these kind of a fuel. It's like a 3-step process, just like the liquid fuel. That's the reason why we have a higher regression rate compared to that of the other fuels. And another one is an extension of this work, which is like to introduce this kind of a concept and see whether we can eliminate the system. So earlier I told reaction dynamics is working on hybrid systems that uses paraffin wax and hydrogen peroxide. So hydrogen peroxide is one such kind of an oxidizer where you bring it to any substance using a catalyst, it ignites spontaneously. So here we have hydrogen peroxide droplet, solid ethanol. When they meet, they ignite spontaneously without having a dedicated ignition system. So this solid ethanol, what we have developed over here, is kind of self-igniting and also having a better regression rate compared to that of the paraffin. So this is the liquid logic what we are going behind, and we will be converting this or expanding this work to kerosene, because liquid ethanol is not that regressive compared to that of kerosene. And in the future, we may go for even gas fuels as well. So our study has limitations, like I cannot claim too much because the work is under the lab scale. The next would be something like on a small thrust stand to actually compare 1-to-1 with paraffin and the solid ethanol. So of course, there would be a question like, I expect that like so far we have, it's more than like 100 years, hybrid is in development, why people are not using it. But recently there is a traction on hybrids for the medium launch vehicles. And there are not much successful tests except this, which happened in 2022. So InnoSpace is again a South Korean startup company in 2018. They worked heavily on both liquid system and hybrids. Hybrids have been used for their first stage rocket, and they use this paraffin wax and LOX. It's a kind of a sample video to show that like how impact it is for the hybrids. So when you build a rocket, the first phase would be testing it in a small scale inside a static fire test stand, evaluate its performance, compare it with the existing data, and then build onto a rocket. So this is called Hanbat TLV, test launch vehicle. So they launched it from Brazil. It's also, again, electric pump. It's a pump-based hybrid rocket engine, which they use to raise the pressure of the liquid oxygen when it comes to the chamber. So the trajectory of this testing is they started with a small thrust, like earlier 50 kilonewton, and then stepped up all the way to 150 kilonewton. That is their range of thrust, what they look for their vehicle. And a couple of other electronic testing, flight hardware, pump testing. And then in, I think in 2023 or December 2022, they launched from Brazil. So this is the first hybrid actually in action for suborbital launches. Of course, this company is going to do it further like launches. It would be an integrated system of hybrid with upper stage of liquid. So this is like a single stage rocket, which is for the suborbital. And about us, our research group, basically Ignite Rocket Propulsion Research at Concordia. We focuses on different subsystem rockets, like for example, hybrid rocket engines, liquids, gels, and in-space propulsion system, and further studying the combustion characteristics at a micro droplet scales and include sprays as well, which would help us in designing the injectors. And the focus is more towards smaller thrust launch vehicles, turbopump design, and then again, high regression fuels, designing of high regression fuels for hybrid engines and also for the gel propulsion system. We have partnership and collaboration currently with NSERC, which is a federal funding agency, and with Phones, the research from Quebec. And also we have an active partnership with Nordspace where we work on turbopump development for their launch vehicles. We have like a MOU with MDA and Reaction Dynamics. Both are in discussion for a future partnerships. Thank you. And I'm open to questions, like if you have.
If you have any questions, just raise your hand. We'll bring a mic over. Got one right here.
Yeah.
Thank you. The fuel configuration, the rounded thing, do you use rare minerals in it?
No.
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 What temperature does it go up to? What temperature?
The fuel temperature or
the metal, the rounded metal that the fuel exits from?
Oh, it would roughly comes around 2,500 degrees Celsius. Oh, Kelvin, sorry.
Okay. There's no rare minerals in that.
No, the metals what we use in the fuel is generally additives, energetic additives. That comes as nano fuel aluminum or boron, carbon activated carbon. All these are the ones which are currently in use for the fuel. But if you're asking about the materials in which the nozzle has been mud, I think it's a specialized alloy. But even if it is for the short thrust duration or short fire duration, even Space Concordia uses the ablative chamber, which eats itself up like carbon based. So we are not using a specialized one so far because we have an active cooling system in the chamber, which would reduce the exit temperature significantly.
Thank you.
Does anyone else have any questions?
For hybrid engines, what do you believe is holding it back, or what specific thing is holding it back from breaking through in the market? And how long, or what do you estimate it will take for it to actually break through?
So this is the start point, like InnoSpace from South Korea is the start point that they have actually shown or demonstrated that it's possible to work with the hybrids. The biggest point in which people are like staying away from hybrids is because of the bad burning. They burn, it's like two different, so in terms of combustion, two liquids mixes up very quickly. It's very miscible, and two gases much better. So combustion happens in the gas phase. So combustion is the one which is releasing energy, converting into thermal energy, and thermal energy would be used to heat up the molecules, and the molecules accelerates in the nozzle to produce thrust. So that process in which the heat energy is released for the hybrids is two different phases. You have a solid fuel, and then you have a gaseous oxidizer or liquid oxidizer. When it comes to a hot temperature environment, this fuel has to go from solid to melts to liquid and then gas, instead of liquid to gas here. Meaning you need a lot of oxidizer for a small chunk of fuel. You're carrying more oxidizers than it is required because of the bad fuel burning rate or regression rate. When you translate that one into empty mass of the entire rocket engine, you can actually develop a pressure-based liquid engine, which is much cheaper and simpler and better performing than that of the hybrids. But what paraffin is trying to overcome is reducing that one. So if you compare the rubber-based conventional hybrid fuel with that of paraffin, the jump is almost like tenfold in terms of the burning. So you have to find some alternative, because paraffin is also having a bit of a problem that once it faces the higher temperature, its material integrity, it doesn't remain solid. It can break off easily. It can just push away through the chamber, through the nozzle. So you will also have a loss of fuel as well. So when you compare that one, of course, paraffin is good, but it's not the best, which can actually overcome the market, like take over the market.
I believe we have time for just one more question, so we'll hand it over.
Thank you. Yeah, so I had a question regarding hybrid engines in terms of their having them being reusable. So just like in terms of their performance in that area, what do you think?
Hybrid is similar to that of liquid in terms of throttability, in terms of cutting off. So the system adapting a reusability system to that of the hybrid is of no brainer, except that the rocket would be like, for this kind of a class, 150 kilonewton thrust, the rocket engine is significantly taller compared to that of liquid. So maybe in terms of the empty mass, that is the factor which will be playing around a bit. Otherwise, it's reusable.
Thank you.
Thank you so much.
Thank you, Jerin. Thanks for coming in. It was great to have you here. We're going to close up the Zoom and the live stream now, but this remains available on our YouTube channel. So you should revisit it, share it, etc. Also, please stick around. We have a few more things coming up. And that's it. Okay, bye.